Hello everyone! Today we will be studying the case of compressible two-dimensional flow over an airfoil, and to have a better understanding of these physical phenomena we will be using Ansys Academic. First of all, we will do a preliminary introduction on the compressibility effect on lift coefficient, limiting our case of study to subsonic flow. We will run in simulations with Ansys Academic using the CFD module Fluent. We will plot graphs on flow parameters and also visualize some simulations. So, what happens when we increase the Mach number up to high subsonic values? In a classic book by Shapiro, we find that as the free stream Mach number increases, the local velocity on the airfoil increases more rapidly than the free stream velocity. In a way, this extra increase in kinetic energy must be paid with an extra decrease in local pressure, having more negative values on the pressure coefficient on the upper surface of the airfoil, implying an increase in the lift coefficient as we see in these graphs. So, here is what we are going to do. We are going to test this theory by running some CFD simulations and actually getting some numbers and conclusions. The airfoil choosing for our study is a typical airfoil. It's an ACA 4412. We are also going to be using sea level reference values for density, pressure and speed of sound, which can be found as a function of temperature with this formula. Now, in order to have some numerical ideas of what actually goes on with the flow over the airfoil, we are going to run some CFD simulations and complete this table. This will help us acquire some interesting plots, trust me. So here we are at Ansys. I have loaded the previous project that I had made for this video. As you can see, I have many Fluent simulations, one for each particular Mach number. Of course, you're going to have to start by the geometry and the meshing. In this video, we are not getting into the detail on how to do that. There are plenty of videos on YouTube showing you how to do it. But I'm going to show you the mesh we are using. This is the mesh. It's a type C of meshing. It's quite famous for this type of airfoils. And as you can see, it's quite structured. I'm going to zoom in. It has a refinement near the airfoil. And it is important that the mesh you use is structured. That will make everything smoother. Okay? So going to Fluent, I'm going to show you how to set up the Fluent simulation for compressible flow. Under General, you're going to hit Pressure Base. You're going to want a steady simulation. Under Models, you're going to hit under Viscous Model, K omega, SST model. This works quite well for airfoils. Under Materials, for fluid, air, take particular attention here. Usually density is set as constant. You're going to want ideal gas. And for viscosity, we choose Sutherland 3 coefficient method. Okay? Close. Cell boundary. Make sure the surface body you generated is set as fluid. Here. Fluid. Under boundary conditions, inlet. Here you choose the operating conditions. This is the sea level pressure. Hit edit. So here you can set the velocity. If you are using a type C of meshing, be careful to choose components and not normal to the boundary, and edge velocity. Okay, going back to mesh, what we are telling the software is that we want the velocity always being in the x direction, okay, and not normal, otherwise the velocity would be like this. So under thermal, we want the sea level reference temperature, which is 15 Celsius, which is this equivalent in Kelvin degrees. And the reference value, we're going to hit compute from inlet. And here in length, it will depend on the chord length of your airfoil. In my case, it is a 1 meter airfoil. Under method, you're going to hit couple. Here is something interesting. You can set up report definitions. I have made a report for CL. The procedure is like this: force report, lift coefficient, make sure to set it on the airfoil, and you're going to hit report file, report plot, and print to console. That way you will see the value of force CL being computed right in here, and also you will see it in a graph as iterations are made. Closing here. Initialization, you're going to hit initialize, and after that you're going to run the calculations. Now the question is, how many calculations do you need? Well, it will depend on the Mach number. For Mach numbers below 0.3, approximately 200 iterations are okay, and it will start increasing from there. For example, for Mach 0.5, you can have 600 iterations, more or less. The problem arrives in here when you compute for Mach 0.8. As you will see later in this video, for this free stream Mach number, you will have shock waves on the airfoil, and that will complicate the things a little bit. But if you leave it computing with the usual setup you have for conversion in Fluent, it will converge by 1,600 iterations. Okay, I saved the image for you to look at. This was the run for Mach 0.8. It converged at this number, like I was telling you, 1,600 approximately. This was the image of the residues, and this was the image for the CL factor, for the lift coefficient. You may be misguided when you stumble upon this, thinking that, okay, I do not need any more computation, but trust me, it will stabilize at some point and the value will converge. So after you have done all this process, you will have the results for all Mach values. You will have the CL for all Mach values. And I'm going to show you how to obtain other parameters, how to easily obtain them. For example, let's hit results, edit. So here you are. As you can see, I already have the contours, but the procedure is like this. You're going to insert a contour, and you will plot any variable you want. Let's suppose we want the Mach number. Domains everywhere, and global, hit OK. And the program will tell you immediately the minimum and the maximum values. You can repeat this for pressure, density, whatever you want, and so you can obtain the values from your flow. Remember that the maximum velocity will be in this zone, and so will be the minimum pressure and minimum density. Okay? Once you're done, this is the result. Now, let's plot these results. For example, here we have a plot for the lift coefficient as a function of the free stream Mach number. As we were expecting, the lift coefficient increases as Mach number increases. Now, you might be wondering, how can you validate these results for your CFD run? Well, there is a simple way, which is to use the Paran-Glauer rule, which corrects the CL of incompressible flow for compressible flow. Of course, the question is, which CL for incompressible flow should we use? We can obtain it from the NACA documents and assume the error to be negligible. In this case, for zero angle of attack, the value for CL is around 0.4. Now, plotting these results, we can compare both curves, and we can see that we obtain fairly similar results, of course having a difference from Mach number of 0.6. This was in fact expected, as the Paran-Glauer rule loses accuracy around that Mach number, as we can see in this graph from Anderson's book. It is important to think about what is the CL. Well, the CL is a manifestation of the complex interaction between the flow and the airfoil, and it's the coefficient that let us estimate lift. So let's not forget that lift is in fact generated by the net imbalance of pressure. So let's see what happens with the pressure as we increase the Mach number. If we focus our attention on the upper surface, we see that the pressure keeps on dropping as the Mach number increases, explaining the change in lift as we expected. You may also notice that for Mach number of 0.7 there is a somewhat low strength shock wave, and that for Mach number of 0.8 we have distinguishing shock waves manifested by a rapid change in pressure. Now, let's see what happens when we move to velocity. Here we have plotted both the free stream velocity and the maximum velocity on the airfoil as a function of the Mach number. It is clear that the local velocity increases more rapidly than that of the free stream. You should also notice that for the point of Mach 0.65 you have a velocity around the airfoil that is somewhat around the sonic speed, and that for Mach 0.7 we have supersonic speed on the airfoil, which will end in a shock wave like we notice in the pressure animation. So we have established that the local velocity increases more rapidly than the free stream. Now it would be interesting to know by which factor. So here comes the following plot, where we see the ratio between the two of them. It is interesting to notice that for Mach numbers below 0.3, the ratio is virtually constant, being the local velocity approximately 30% more than that of the free stream. Why is this important? In this next slide, we plot the pressure on the upper surface too. It is clear that pressure remains virtually constant for Mach numbers below 0.3. Thus, if we bring back the plot for CL, we notice that it also remains virtually constant for low Mach numbers, starting to rapidly increase from Mach 0.3. This value is usually the one taken for dividing incompressible from compressible flow. Now let's see what happens in the animation of velocity. Indeed, we see the rapid changes with increase of Mach number and the shock waves by the end. Moving to density, this is the last parameter to analyze. Clearly a density drop is what we are looking for. Here it is plotted the ratio of the minimum density of the airfoil to the free stream density. We can also see the plot for the local Mach number. This plot gives us a surprise. The shock waves don't necessarily occur at Mach 1. We can have supersonic Mach numbers before nature accommodates itself. One way to check the results within them is to apply the expression for isentropic evolution. While the flow is shock-free, the total density is constant, and we can obtain the ratio of densities by replacing the Mach numbers. By doing so, we obtain a fairly similar curve. Here is the animation for density. And last but not least, let's see all three animations together. Now, for conclusions, what do we have? Well, for values of free stream Mach number up to 0.3, we have the ratio of maximum local velocity to free stream velocity is virtually constant. The static local minimum pressure and local minimum density are also virtually constant, and the flow can be considered incompressible. Now, for values of free stream Mach number higher than 0.3, the ratio of local maximum velocity to free stream velocity increases more rapidly. Also, the static local minimum pressure and local minimum density drop, and compressibility effects are not negligible and impact on airfoil parameters. On the other hand, shock waves don't necessarily occur at local Mach number 1. Rather, supersonic flow may occur before nature accommodates itself. And for last, the CFD proved to be a valuable resource in understanding the physics involved, with results matching the theory. Well, thank you very much for watching, and I hope you found this video quite useful. Bye bye!